So today we are covering water, or at least beginning the discussion of water. As we talked about in the last lecture, water is absolutely vital because most reactions for living organisms occur dissolved in water. Not living organisms dissolved in water, but the macromolecules that compose living organisms are dissolved in water. Water is everywhere. Everywhere you look, there's water. If you look out the windows, here, I'll open the window, and out there are trees, and those trees may look very solid, but 95% of that plant mass is water. You are pretty much a big bag filled with water. 70% of you is made of water. 75% of the whole earth is covered in water. The air we breathe has water in it, water vapor. When you breathe out, there's a whole bunch of water vapor. Water is absolutely everywhere. It's going to be important for biology because water is the medium in which most chemical reactions occur. You have these things called macromolecules. So micro means small. What does macro mean? Big. Big molecules get dissolved in water. The way that works is here we've got a big thing of sugar. You guys have seen sugar crystals before, right? You take them, you put them in your coffee. Salt. You can see a grain of salt. It's not microscopic. But they're made up of subunits that are all attached together. When you put them in water, water is able to dissolve them. Water is able to break them apart. They work by, so usually these substances are going to be ionic. They're held together by sort of an interaction between a cation and an anion. And water is polar. It's got a positive side here and a negative side there. So the positive side of the water is going to be attracted to the negative side of the chemical, and they'll start to sort of break things up. My wife wasn't feeling well yesterday, so she said she needed a hug. So she came over and she gave me a hug. Now I have children, and what these children do is they decide that's not appropriate. So as I'm hugging my wife, I feel two sets of hands getting in between us, forcing us apart. That's what water does. If you've ever been to a party, and I had to do this for my friends previously, you don't want two people to sit together because they're bad for each other. You've been that person. You've made that judgment call on your friends before, haven't you? That's what friends are for. They are there to make sure that other friends don't do stupid things and don't date stupid people. So what do? You make sure those two people are never together alone. You sit right in between them in the couch, as if it was and you do it in the most obnoxious way possible. They're sitting there, they start to cuddle, and you come in and you literally you just shove yourself right between. You're like, so, how's it going? And then another person comes, because they're in on the plan, and they push them farther and farther apart. That's what water's doing. It's breaking apart these molecules, forcing them apart. So we've been saying things are dissolved in water. You've created a solution, but a solution has never been defined. You have different components of a solution. You have a solute. The solute's the stuff that dissolves. Salt, sugar, Kool-Aid. In this case, cupric sulfate is this blue coppery substance that it makes Smurf water, I guess. If you were to take that solute, you would put it into a solvent, which is a liquid that does the dissolving. It could be water, could be alcohol, could be oil, could be anything. As you put the solute in the solvent and stir it, it dissolves. It disappears. You don't see a pile of solute down here anymore. It's gone. It's completely dissolved. All the molecules are broken apart and shoved separate. So that creates a solution. The solute dissolved in the solvent. In biology, we talk about, usually we talk about aqueous solutions. An aqueous solution forms when water is the solvent. Not all solutions are aqueous. Some molecules don't dissolve readily in water, but they'll dissolve readily in other substances. Think nail polish. You guys ever painted your nails before? Okay, some of you have, some of you haven't. Let's say, I don't know, it's a Sunday afternoon, and your daughter's super bored, and you do anything to shut her up. So you sit down, and you let her paint your nails. You don't, this is all hypothetical, by the way. You let her paint your nails, and she does a good job on it. She works for it in a while. But then you have to get it off before work on Monday because you're going to see students at 8 in the morning, and then again at 9:30. So what do? You have to remove it. Does water remove nail polish? No. What do you have to use? Yeah, nail polish remover, right? Isopropyl alcohol. If you were to take this alcohol and put it on that nail polish, what happens is the nail polish starts to dissolve. It starts to go into solution. So when you remove it with a cotton swab or something, it comes off easily. So you have one type of solvent that can get rid of a particular chemical while other solvents cannot. In biology, we usually don't mix things well with alcohol. Biology and alcohol don't mix, except when you're studying sometimes. Instead, you're going to form solutions out of water. And those solutions are going to be termed aqueous. Think aqua, water. Salt in water, so salt water, ocean water, is an aqueous solution. Now water is kind of special. It's got these things called colligative properties. These properties depend not on the type of solute that you put in, but on the amount of solute. How many solute molecules are present? And they change things like the boiling point, the melting point, the freezing point, and the condensation point. So the melting point, so we've got, let's say, the boiling point or the vaporization point, which is the same as the condensation point. Then you have your melting point, which is the same as your freezing point. Now in water, what is the boiling point of water? 100 degrees Celsius. Say it again? 100 degrees Celsius. Thank you for using Celsius. It's so much easier. And Fahrenheit wasn't like 232, something like that? Nobody knows. Fahrenheit makes no sense whatsoever. So that's going to be the same as the condensation point. The point at which water boils is also the temperature at which water vapor turns into a liquid. How about the melting point, or the freezing point? 0 degrees Celsius. And you guys, of course, know the freezing point of water, right? In Fahrenheit. What is it? 32. And you know that from all of those years looking at the weather, hoping school will be canceled. Because you know, in Pennsylvania County, when it gets below 32, there's a really good chance that school's not happening. If you were to add solute, you can change these properties. You can add salt to boiling water. Why do you add salt to boiling water? Some people do. It heats it up faster, right? The boiling point is lower. So now instead of cooking at 100 degrees, you cook at 98 degrees. So, prior to meeting my wife, I did not know that broccoli was supposed to be green. I know, crazy, right? Everyone's like, green broccoli, but my mother would cook broccoli, not just at 100, she would cook it in a pressure cooker, so well above 100 degrees. And it would come out gray or white. So, kind of gross, but that's the way it was. So I had no idea. You can change cooking temperatures based on how much solute's present. How about this melting freezing point thing? Is there a practical application? Yeah. You guys have seen salt trucks go out, spray salt all over the roads, haven't you? So these salt trucks go out and spray salt. They do that in order to decrease the melting point, the freezing point, down to 28 degrees. So now, ice will melt at 28 degrees instead of melting at 30. You have a faster melt time. Additionally, the freezing point of that road has dropped. So the temperature has to be colder for that area to freeze. Works out kind of nice. In nature, so this depends on the type of solute, not the, on the amount of solute, not the type of solute. We use salt in the roads. Why don't we use sugar? Sugar will do the same thing. Why do we use salt?
It just makes them sticky afterwards.
That's actually a really good point. Don't have to worry about ants. That's nice. It's not sticky afterwards. Those are more. That's a good reason, but there are other reasons that are probably more pressing for like the city council.
Larger crystals?
Say it again.
They're like salt's larger than sugar would be?
The salt is a smaller molecule than sugar. The crystal themselves, they may be larger, but that doesn't matter because you're going to dissolve it in water.
So probably more expensive.
What? There you go. Price. Salt's crazy cheap. Sugar, not so much. So you can buy more salt than you can buy sugar. Also, salt is a smaller molecule, which means that you can fit more molecules in the same space. In nature, we can use colligative properties for all sorts of things. Organisms use them primarily to survive cold temperatures. Here we have the springtail. The springtail is one of the only organisms to survive in Antarctica year-round. It is a type of, almost a gnat. What they do is they lay eggs, put their larvae in melt ice. Now these larvae would normally freeze right back up. But they're constantly producing almost antifreeze in their bodies. They're producing a bunch of solutes. And those solutes get dispersed through their bodies and prevent them from freezing. Because their bodies can stay, the freezing point of their body is going to be lower than the freezing point of the ice, the water around them. So even if it iced all the way around them, they would be fine. The parasitic wasp, which by the way lives in Danville. I'm a biologist and I've still yet to figure out the purpose of wasps, aside from to annoy me. What it will do is it will come along and it will sting a caterpillar. And into this caterpillar, it will inject little tiny eggs, and as well as some solutes. Now those solutes will allow the caterpillar to survive in the cold. Because now the caterpillar has these lower freezing points in the area around it. Downside is there are also eggs hatch inside of it, and they start to eat their way out of the caterpillar from the inside out. So it's sort of like an incubator for the eggs. It just wants to die, and it can't. Until eventually the larva burst out of its sides. The rock cod. The Atlantic rock cod looks like ice. It survives by living right up along the ice sheets that extend into the water in the Arctic Circle, the glaciers. So you've got ice sitting on top of water. The water down here is really, really, really cold. In case you didn't know, don't go swimming in the Arctic. Bad idea. If you don't have specialized adaptations, you can't survive. The rock cod is able to produce a whole bunch of solutes that act like antifreeze, so that its body is it has a lower freezing point than the water around it. What's the temperature of the water near the top of the ice in the ocean? 0, okay? Because right there it's ice, right? It's actually not 0. Is it higher or lower than 0? Lower than 0. It's below freezing here. Why? Not just because it's under the ice. Because if it was below 0, what do you expect to happen at 0? It freezes, right? But it's not freezing. Why is it not freezing? It's because it's salt water. So you got this salt in the ocean water, which lowers the freezing point. So that's below freezing temperatures. If the fish didn't have those specific solutes going through its body, it would not be able to survive. It would turn into, you guys, I hope, you played Mario Brothers, right? If you play Mario, if you haven't, you've lost out on your childhood. There's this one point you get the ice flower. You shoot a fish with the ice flower. What happens to that fish? Yeah, you all knew that. It turns into a block of ice and then floats up. That would happen to that fish, except it's got these solutes in it. One more thing, and then I'll let you guys go. And I was reading about it last night, so I have to tell you. There's this particular type of shark called the Greenland shark, or the Pacific sleeper shark. It's a huge shark and it's very slow moving. The only way it survives in the Arctic cold waters, where most other organisms cannot thrive, is because it is putting out uric acid crystals to all of its organs. You cannot eat this shark or you're going to be poisoned by this uric acid. So pretty much uric acid is the same stuff, urea, that you put out in your pee. So pretty much they get this shark out of the water, it smells like urine, The Scandinavians said, I would like to eat this. Well, they can't eat it. I don't know why. It smells like urine. They pull it out. They want to eat it. They can't because it's so poisonous. So what they do is they bury it underground for 6 months. They let it rot in order for that uric acid to break down, and then they eat it. It is a specialized national dish in Scandinavia, and apparently it has been voted on as the worst dish that has been served in the world. So, in case you ever want to know what a urine-filled, decayed shark tastes like, they actually offer a dish on it. I will see you later. Good. So, to pick up from last time, just a brief review. We're going to go over some stuff. We have thus far talked about water. Now, water is everywhere, as we talked about. You're primarily made of water. The trees are primarily made of water. Everything's made of water. It's awesome. We started talking a little bit about the nature of water, the colligative properties of water. Now, colligative properties. Anybody want to take a shot at what those are? Of course not. Just took a quiz. Right, so they totally depend on the amount of solute rather than the type of solute. But what do they affect? Melting and freezing points, the boiling point, the vaporization point. These are going to be colligative properties. So if you were to add salt to water, what does it do to the boiling point? It brings it down. If you add salt to, ice, it reduces the melting point so that water will ice will melt then at 28 degrees instead of at, say, 32 degrees. So we talked about basically colligative properties. We talked about a little about water. We talked about the idea of a macromolecule. What's a macromolecule? Not trying to trick you. It's a big molecule. There we go. That's the answer. We're going for a big molecule, macro. So we've got these macromolecules. Those macromolecules are going to be dissolved in water. That means you're going to need two things. You need a solute and a solvent. In salt water, what is the solute? Salt. Well done. What's the solvent? Water. Put them together, you have a solution of salt water. There we go. There are special types of solutions. These solutions are made using water as the solvent. What are those called? Aqueous solutions. Thank you for being so on the ball. That's exactly right. And that should catch us up to right here in the water lecture. Do you guys have any questions? Today we're going to go through a lot. So, water is a polar covalent molecule. Polar, what does that mean, polar? That's right, it's got poles. There we go. So we got a north pole, we got a south pole. Or in this case, we got a positive pole and a negative pole. Oxygen has an extremely high electronegativity. Okay, I've emphasized this several times in the course already, and I'm going to keep emphasizing it. What is electronegativity? Not other atoms. Electrons, you win. That's exactly right, and I need you all to know that right off the top of your heads whenever I ask. Because electronegativity comes up again and again and again. The propensity of an atom to pull electrons unto itself. It's sucking in electrons. Oxygen is hugely electronegative. There's lots and lots and lots of electronegativity there that suck electrons to it. Thus, in this molecule, oxygen is pulling all the electrons in, making the area around oxygen negatively charged. Well, because of that, you got hydrogen and hydrogen, right? Those two hydrogen atoms, they don't have their electrons hanging out with them anymore. So what are they going to have? A positive charge. Now, this isn't ionic. They're not stealing electrons. They're still sharing. So it's covalent. But you have a positive side and a negative side. And that's what leads to a lot of the properties of water. All right, now because of that polar covalent nature, water can interact with molecules in three different ways. Water can be hydrophilic, hydrophobic, or amphipathic. To be hydrophilic, philia. Have you guys heard that term before, philia? What does philia mean? It means to love, to hold dear.
There's all sorts of philias. You guys probably hear them in relation to, I don't know, weird procedural cop shows where people have all sorts of super awesome philias that really should never be talked about. Hydrophilic molecules love water. They tend to be polar. They tend to have a charge to them. They tend to have positives and minuses. They tend to have a side that has too many electrons or a side that has too few electrons. And then to dissolve these hydrophilic molecules, what water does is it surrounds them and it binds to those regions that are positively or negatively charged. That helps to dissociate the molecule, to break it apart. We talked last time about a small child getting in between two parents and pushing them apart. Or you coming in and, I think we talked about this anyway, you coming in and you've got friends, right? Some of you guys do. If you have friends, and if you don't, sorry, this may not really get this, but you've looked out for your friends before, right? They've dated people that you were like, no, that should never happen. Or, now we know, thanks for the look. There are people that you look at and you're like, I really don't want these two people to get together. So what do? How do you stop them from getting together? You try to break them apart, right? If you've been at a party, again, some of you guys may not understand this, but if you're at a party and these two people are going to sit together on the couch and they're going to have a moment, what do? That's exactly what you do. You come in here just like, hey, and you squeeze yourself in too. You're not even subtle about it. It's like, watch out for that cord. You get in there, squeeze in, and you're like, how's it going? And you're right in between them, and now they're spread apart. And if you've got friends, more friends, and you may or may not, they might get involved in this too, and then get between you and the other person until finally, by the end of the night, those two people who are trying to have that moment together are completely separated. It's the exact opposite of, I think, that scene in The Little Mermaid, Kiss the Girl. Totally the reverse. So why did I go there? So that's what water does. Water gets in between these macromolecules and splits them apart. This picture is wrong, and I'm sorry for that. Take a look. It's kind of weird. You got these hydroxide molecules that have negative charges attracting the water molecules, and they break apart glucose. Now, why is that picture wrong? What's wrong with it? So if you look here, what's wrong with this picture is oxygen, this big molecule, is extremely electronegative. So all those negative charges, all those electrons, are hanging out by oxygen, making that side negatively charged. That high side is also negatively charged. So how should it interact with the oxygen? It should repel. So how would we fix this picture to make it right? That's right, yeah, you're doing it with your hands. Flip it around. Flip that water molecule around so the hydrogen are facing the hydroxide. The positive side attracted to the negative side. Sorry. Big picture here, though, is that these water molecules are going to get into a macromolecule and break it up. They're going to dissolve it. That's hydrophilic. They break it into its individual constituent parts. Then you have hydrophobic molecules. Phobia. All right, you guys know the word phobia. What does that mean? Scared of, fear, right? In this case, it's scared of water, fear of water. Hydrophobic molecules are typically going to be nonpolar. They don't have a place for they don't have a place for water to bind. There's no ions. There's no charges at all. So water doesn't really bind well to it. Typically, they're made up of molecules that have very, very similar electronegativities. Carbon and hydrogen, over and over and over again. Carbon and hydrogen have similar electronegativity, so how do they share their electrons? That's a question. They take them, they share them, but they share them very, very evenly between both, so that each electron is spending an equal amount of time around each of those constituent atoms. One example of a hydrophobic molecule is oil. What happens when you mix oil and water? They separate. You can like shake up like salad dressing, and eventually it'll get into what looks like a mixture, but it won't ever get into a solution. It won't dissolve. So hydrophobic molecules do not dissolve readily in water. but they could dissolve readily in other solvents. Nail polish, hydrophobic. It repels water. It does not dissolve readily in water. But if you were to apply ethanol to nail polish or isopropanol to nail polish, it goes into solution. So that's an example of a hydrophobic molecule. Oil is a hydrophobic molecule. You can't break down oil very well with water. Heck, there's grease. Have you guys ever gotten grease on your hands? You get grease on your hands, it takes forever to get off. You run it underwater, and what happens? It just beads off and falls. Do you guys know how to get oil or grease off your hands? What do you use? Dawn. Lots of soap. We'll get into soap in a second. The other thing is there's that product called WD-40. You guys know WD-40? Heard of that? You spray it and things stop squeaking. WD stands for water displacement. And that WD-40 actually ends up dissolving grease as well as repelling water. And the final classification is the amphipathic molecule. Amphi means both. You've seen it in amphibian, both land and water. Amphipathic molecules have both a polar side and a nonpolar side. They have both. They are amphipathic. They both love water and hate it at the exact same time. What happens with amphipathic molecules is that they will, let's say this particular amphipathic molecule is what's called a phospholipid. For those of you who have taken the course previously, phospholipids are super, super important, as you know. For those of you who have not taken it, this is your first time taking biology. You're going to see a lot of this because these phospholipids are what make up the cell membranes. So what happens with the phospholipids is you have a polar head and a nonpolar tail. The polar head loves water. It loves it a lot. So the water molecules hang out up there by the polar head. But you got lots of water everywhere. They don't work well with the tails. So when you drop a whole bunch of phospholipids into water, they start to form these structures where the heads face outwards and all of the tails face inwards. These structures are also called micelles. So you have this hydrophobic region and then a whole bunch of water out here for the hydrophilic side. Soap kind of works this way. Think about soap. Have you guys ever washed dishes? Some of you are like, yes, and some of you are like, that's somebody else's job. When you wash dishes, typically you need to get some grease off. You just, let's say you cooked a bunch of bacon because bacon is awesome. Thanks, we really appreciate that. If you cooked a bunch of bacon and you let it sit for any amount of time, what happens to the stuff in the pan? It hardens, it turns white, and then it's harder to wash, isn't it? How do you wash it? Do you just run water over it? No, you have to, if you run water over it, that grease sort of repels the water. You get it hot enough and it becomes a liquid, but it's still there, it's still stuck on there. So you have to get it off using soap. So what you do is you take these soap molecules, just sort of like this. Those soap molecules are then going to form a bubble around your hydrophobic grease. So by scrubbing, that mechanical action of scrubbing, you break apart the molecules of oil, and they then interact with these molecules of soap to form little micelles surrounding a hydrophobic center. That's what allows the grease to go down the drain and keep going. What if you don't use soap? What happens to the grease when it goes down the drain? It clogs up the whole sink, and then you try and get it out, and it's like you're pulling out a small rat. You know what I'm talking about? If you've ever had to clean out a sink, it's like there's a small, gross, disgusting rat that went down the sink and lived there. Because I don't know how hair gets into the kitchen sink, but apparently it does. You can form these structures. You could also form what are termed bilayers. If you were to have water on one side facing those hydrophilic heads, on the other side, you might have water facing hydrophilic heads, and then you have this, what's called a bilayer, because bi means two layers of phospholipids. This is what we're going to see in our cells later. So ultimately, water can interact with a molecule in one of three ways. The molecule can be hydrophilic. That means it's going to be polar or charged and easily dissolved. It could be hydrophobic. That means it's going to be nonpolar, similar electronegativities, and it will not dissolve in water. Or it can be amphipathic, where it's got both a polar part and a nonpolar part, and form these bilayers or micelles. Questions? So if I was to give you a container and it's got some sort of solute in it, and it does not dissolve, what would you term that? Hydrophobic. And if I was to give you a container of, I don't know, sugar, what would you term that? In water. Hydrophilic, it dissolves readily. Water has several important properties that I'm going to expect you to know. I hope to be able to, we're going to go through these fairly quickly so that I can get to the real meat of today's lecture, which is all about acids, bases, and buffers. So here's what we got. We got water takes place in many chemical reactions. Water is incompressible. You cannot squish it down. Water removes waste from organisms. It can evaporate at room temperature. It has a high specific heat. It forms droplets that are cohesive and adhesive. And it expands when it freezes. We're going to go through each of these one at a time. Each of these properties is what allows life to exist. Because of that polar covalent nature, because of the way water molecules will bond with each other, you get these awesome, unique qualities that other molecules don't have. And this really encouraged life to form. If you were to go on to take Bio 102, we talk a lot about possible beginnings of life. By the way, Bio 102 is probably the biology class you really expected and wanted. That's where we talk about animals and evolution and all that fun stuff, plants. Now we're just going through the chemistry in order to get us there. So first off, water takes place in many chemical reactions. You have two big kinds of chemical reactions: hydrolysis reactions and condensation or dehydration reactions. Water is involved in both of these because remember, the environment in which most chemical reactions occur in the cell is water. Most reactions occur dissolved in water, aqueous solutions. The first reaction, those hydrolysis reactions, are using water to break apart the large molecule. So here we got two chairs. Here's a chair, and here's a chair. These chairs form a single macromolecule. Stupid cord. They form a single macromolecule, one big molecule. Make sense? What we do is we'll add some water. So this is the reactant and water. You add water, and it splits them. It breaks them apart. Lysis means to break down. So what you're doing is you're breaking down this molecule into two constituent pieces. Hydrolysis reactions are going to take one big molecule, add water, and then that yields two smaller molecules. Questions on that? This is another, if you want to make sure you know key concepts, this is a key concept. It'll come up again and again and again and again. Hopefully you only need to learn it one time, and then we're going to learn this and then give it new names later in the course. But this is the basis of a lot of biological reactions. Condensation reactions are just the opposite. You have two reactants. You end up removing water from them. You dehydrate it, and then they form a single macromolecule. Questions? So add water, hydrolysis occurs. The molecule splits. Remove water, dehydrate it, and you have condensation. They condense down. Questions? Well, this is just water, right? I'm stealing it. All right, so macromolecule. Put some water on, and oh, look, it splits. What kind of reaction is that? Hydrolysis. You remove the water. Sorry. You remove the water. and they come together. What kind of reaction is that? Condensation. Thank you. Concerns about those two concepts, because like I said, they will come up again and again. I hope nobody sits in these chairs later. Oh, or if they do, I hope it's someday I don't like. Water is incompressible. It doesn't squeeze down. Organisms use water to support their structure. So if you've ever, you can take air, you can take gas and condense it. That's how you can take all of these, like a mixture of gases, and put it in a scuba tank. You could squeeze them down tighter and stick them in a steel tank. No problem. You can't do that with water. Water does not compress down. So plants and certain organisms use that property in order to maintain their internal structures. Those trees would not be able to hold their form without water. Think about plants. What happens when they don't have water? What happens to them? They wilt. They lose their structure. Water is used to eliminate waste. You go to the restroom and what comes out? Liquid waste, carrying with it all of those things that your body can't process. Someday I'm going to write a whole lecture about why your pee smells after you eat asparagus. That's my goal for 102. Because it's an important lesson that I think we all really want to know about only when we eat asparagus. If you've never eaten asparagus, eat a vegetable sometime. In case you didn't know, these are urinals. They exist in the men's room. There is a protocol for using these. For instance, let's say the door is right over on this far left side. Which one do you go to first? That's right. See, you know this. You go way down there. Where do you go to next? The next person comes in. Where do they go? They just skip one? Okay, guys, where do they go? All the way to that side. That's right. Then where do you go? Right dead middle. Okay, now here's the top question. What do you do if you've got 1, 2, and 5? I'm sorry, 1, 3, and 5. That's exactly what you do. Or you find a stall, but nobody uses stalls. You wait. Or there's a sink, whatever. Water is used to eliminate waste. Water evaporates at room temperature. That's kind of important. If you ever left a glass of water sitting out on the table, after a few days, there's no more water. It's like it disappeared or was drinking by water gnomes. Random motion of the water molecules can excite them enough to break the hydrogen bonds that connect them together. So, in order to understand this, we've got to think about heat and kinetic energy. All right, first off, what happens when an atom absorbs energy? Right, the electron the electron cloud expands. The electrons are moving faster. You've got some energy in there. If it goes too fast, suddenly that molecule can break the hydrogen bonds that are holding it to the other molecules and float away. And as it floats away, it's taking with it that excess energy. So you heat up, you add some energy, the electron cloud expands until finally that hydrogen bond breaks and it flies off, taking with it the excess energy. Well, heat is just kinetic energy. So for you, you sweat. I know, you don't like to admit it, but you do. And when you sweat, you got little droplets of water on you. Those droplets of water absorb your excess kinetic energy, your excess body heat, and then they're going to break those hydrogen bonds, holding them onto each other, and float away. And as they go, they're taking with you that excess energy. You get out of the shower, you're covered in water, and it's colder in the house. It feels that way, doesn't it? Because what's happening is those water molecules are taking your heat away from you. It's a big reason why we sweat. Kind of cool note, if you've ever accidentally licked your own sweat, and you have, what does your sweat taste like? Salty, for all of you guys willing to admit that you've licked yourself. Your sweat is salty. Because it's salty, what you've done is you've changed the colligative property of the water, right? You've changed the vaporization point. You've lowered it, making it even easier to evaporate out. Salt water evaporates much faster than pure water because of those colligative properties. Water has a very high specific heat. It takes a lot of energy to heat up a body of water. Heck, you can just look at that on your stove. If you were to take a metal pan, which has a low specific heat, and put it on a stove, put some water in it, which gets hot first, the pan or the water? The pan gets hot very, very quickly. The water takes a long time to heat up. When you go to cool down, you pour the hot water into a different container. Which cools down first, the pan or the water? The pan cools down really quickly because it has a low specific heat. It takes a long time for that water to cool down. You guys have probably at some point in your life, when you were kids, you wanted to play in the sprinkler, right? You pulled out the hose. On a hot summer day, tell me about that hose water. When you first turn it on, it's like scaldingly hot, isn't it? That's because you've got just a little bit of water in that hose and it heats up quickly. If you had a lot of water, say a pool, when is a pool warmest to swim in? At night. During the morning, it's pretty cool because over the night, it released some of its energy. But during the day, it will slowly gain that energy back. Then you can swim pretty late at night, and the temperature in the pool stays the same for far longer than the temperatures in the environment around the pool. Deserts are formed because there is a lack of water. If you've never been to the desert, do you know anything about desert temperatures? Deserts are hot during the day. During the day, they give off the sun strikes them and they heat up very, very quickly. They have a very low specific heat. But what happens at night? It's freezing cold because there's no water there to stabilize the temperatures. So just as quickly as it heats up during the day, it cools down at night. You see the exact opposite effect around lakes and around oceans. A lot of life spawned around oceans because temperatures are stable. Have you noticed that when it rains, it'll rain during the day, and the temperature during the day and during the night are pretty much the exact same? If you don't, you'll notice it from now on. The temperature is stabilized by the more water that's in the atmosphere. If you live around a lake, you're going to have a lot of water in the atmosphere, so your temperature is going to be stabilized. Water droplets form molecules that are cohesive, and they're also adhesive. Cohesion, water molecules, water drops, stick to each other. You see them sort of like roll and hit each other and then stay together. That's because those water molecules are polar, so you got the positive ends and the negative ends attracting, holding on to each other. That allows water droplets to form. This is also what allows plants to draw water from their roots, because effectively what's happening is water is being sucked up from the roots because it's being released from the leaves. Adhesion. Water droplets will stick to nonpolar surfaces. This is when you see the meniscus form in lab. Those water droplets are holding on to the nonpolar parts of the graduated cylinder. I think there's one more. Water expands when it freezes. This is super cool, and this is what actually allows life to go on Earth. Most molecules, when they get colder, when they lose energy, they condense. They get denser and denser and denser, and the more dense they are, the heavier they are, and they sink. Now, if that was to happen with water, what would happen is in winter it freezes. Ice contracts and it would sink if the colder it got, the denser it got. And then sitting at the bottom of the ocean, you just have layer after layer after layer of ice. But that's not the way it works. Water, because of the polar nature of it, is not only attracting itself but also repelling other water molecules. So as it cools down, as you lose energy, it condenses and gets denser and denser and denser right to about 4 degrees Celsius. And at 4 degrees Celsius, it sinks. It's still liquid. As it gets colder than 4 degrees, it becomes less dense and begins to float. So when it finally freezes at 0 degrees, the ice is floating on the top. And you've seen this in, if you were to get a drink, you go anywhere, you get a drink filled with ice, the water will sit at the ice will sit at the top of the water. Questions on that? I mean, that's the way water works. So because of that, you've got these massive icebergs that can float. They're land masses. They're huge. Some of them are the size of like Rhode Island. And they're floating on the water because they are less dense than the colder water underneath them. It allows for lakes to freeze. And when lakes freeze, they freeze only at the top. They don't freeze all the way through. If they did freeze all the way through, all the life in that lake would die. So they only freeze for, they might even freeze 6, 7 feet down. You've got a solid sheet of ice, but under that ice, you have liquid water that fish and amphibians and reptiles can survive in. It's kind of cool. Turtles hibernate. You knew that, right? So it's surprised if you didn't. And a lot of them will hibernate at the bottom of bodies of water. And the way they do that is they'll swim down to the bottom. They take a deep breath, swim down to the bottom, and this happens in the Dan River, actually. They'll sit on the bottom and put their body into what's called a torpor, which is where most of their systems slow down a lot. And then if you've ever seen a turtle, you know how they stick out their neck and they got that weird webbing thing right by their neck? They actually are going to allow oxygen molecules from the water dissolve through that, and they can keep their systems going. So they're pretty much in suspended animation underwater, just getting these oxygen molecules. But they wouldn't survive if the area froze. They only survive because that area underwater is slightly warmer than freezing. Oh, and because of that, universally at the bottom of the ocean, it's 4 degrees Celsius. So there we go. Water takes place in many chemical reactions. You've got condensation reactions and hydrolysis reactions. Absolutely vital that you know that. It's incompressible. It helps remove waste from an organism. It evaporates at room temperature, allowing you to cool yourself down. It has a high specific heat. It forms droplets that are both cohesive and adhesive, and it expands when it freezes. So that's the basics about water. I want to get into how you can determine the amount of solute present in water. This is going to be important for determining yields in chemical reactions. It will also be important for understanding the basics of acids, bases, and buffers. So your solute concentration is the amount of solute dissolved per unit of solvent. That's the textbook definition. How many of you guys have taken chemistry before? If you've taken chemistry, what we're working now is moles and molarity. And if you've taken chemistry, you probably hated moles and molarity. I'm going to give it to you as easy as I can give it to you. And some of you will look at this and be like, oh, really? Is it really that easy? So here we go. Solute concentration. It's the amount of solute per unit solvent. So here we have, what do you think's in the cup? Coffee. We're going with coffee then. And the yellow packet, do you guys know what the yellow one is? Splenda? All right. So we have a packet of Splenda and a cup of coffee. So far, so good. How many packs of Splenda are per unit of coffee? You would say it's 1 pack per cup. So far, so good? Questions on that? That's solute concentration, 1 pack per cup. What if we added 3 packs in? Then what would we have? 3 packs per cup. Questions? So far, so good. All right. Now, let's say we wanted to make 5 cups of coffee that have 3 packs in it. How many packs do we need? 15 packs. Questions? I know. That's all we're doing. That's all this works. So instead of saying, I don't know, packs of cups, let's go with liters and grams. So 1 pack equals about 1 gram of that Splenda. So if I was to put in 5 packs of Splenda into my cup, how many grams of Splenda are in my cup? 5 grams per cup. Make sense? Questions? Concerns? That's all solute concentration is. Now, we're not going to typically talk about things in packs. We're going to talk about them in levels of grams. Now, there comes a problem, though, because, of course, it can't be that easy. It's easy to compare the weight of two different types of molecules, or two different solutes. The problem, though, is that the different solutes each have different molecular weights, which means you're going to have a different number of molecules per unit volume than you would have in one substance than another. For instance, hydrogen has an atomic mass of 1, right? Oxygen has an atomic mass of 16. 1 gram of hydrogen would have a lot more hydrogen atoms than 1 gram of oxygen, because they're bigger. It's sort of like saying, oh, I've got an elevator. All right, the elevator weight limit, and you guys know you always look at that weight limit and then start gauging how big people are that come in. So you've got an elevator that's got a weight limit of 2,200 pounds. You could put in there 22 people that each weigh 100 pounds. You could put in there, I don't know, I'm doing some quick division, sorry. 4 people that each weigh 550 pounds. You have one group, both weigh the same. 22 people that weigh 100 pounds or 4 people that weigh 550 pounds. They weigh the same amount total. But you have far more of the smaller person than you have of the bigger one. That's what would happen with measuring the numbers of molecules per unit of weight. So to account for that, we came up with the idea of molecular mass and moles. Okay, real quick, another way, instead of looking at the elevator, you know the old idea that which weighs more, a ton of bricks or a ton of feathers? What's the answer? They weigh the same, right? Ton of bricks equals a ton of feathers, but which will have more individual units, the ton of bricks or the ton of feathers? The ton of feathers will have a lot more to it, a lot more individual units. We need to get to a point where we can accurately compare the numbers of molecules per unit of measurement. So we're going to start off by figuring out the molecular mass of the molecule. To determine the molecular mass, you take the sum of all of the atomic masses of that molecule. The molecule we're going to look at here is NaCl, sodium chloride. So NaCl. How many sodium are there in that molecule, NaCl? 1. How many chlorine? 1. So what you're going to do is you're going to say, all right, how much does sodium weigh? Let's round it to the nearest whole number. 23 AMU. Important to put those units. 23 AMU or 23 Daltons, either way. For chlorine, nearest whole number. 35. Good, because there's a 4 there. Well done. So you have 35 AMU. 23 plus 35 equals 58 AMU. So the whole molecule, here you got 23. Here you have 35. The whole molecule equals 58 AMU. Is anybody lost in how I got that? The next step is convert that to moles. The definition of a mole is the molecular mass of the molecules expressed in grams. All right. What's the molecular mass of NaCl? 58 what? No. AMU. How much does 1 mole of it weigh? 58 grams. All you're doing is converting 58 AMU to 58 grams. So 1 mole equals 58 grams. Questions on that? 1 mole is also equal to a specific number of atoms or a specific number of molecules. I want to say it's 6.02 times 10 to the 23rd power. But does anybody know Avogadro's number off the top of their head from chemistry? If not, I think it's 6.02. Yeah, okay, thanks for backing me up, because I'm not a chemist. Neither are you, so there it works out. We'll just confirm each other's beliefs and go with it. I think Avogadro's number is 6.02 times 10 to the 23rd power. That is a huge number of atoms. And so what 1 mole represents is the molecular mass expressed in grams, and it is equal to that specific number of atoms, that specific number of molecules. So 1 mole of sodium chloride, 6.02 times 10 to the 23rd molecules of it, weighs 58 grams. But we can't do much with that. That's just a big pile of salt, right? What we're going to do next, we're going to take that 58 grams and dissolve it in water, because this is the whole water lecture. When you take 1 mole, 58 grams of salt, and put it into 1 liter of water, you've created a 1 molar solution of salt. All right. That's how you determine molarity. I know. You went over it forever in chemistry, and it seemed a lot harder then. It might seem really hard right now. Let me ask you, how would you make a 2 molar solution? Pardon? Multiply by 2, and so what's the answer? 58 times 2? 1 what? 16? Well done, yes. 116 grams into 1 liter of water. Because all you do for 2 molar solution is put 2 moles of that substance, which is equal to 116 grams, into 1 liter of solution. How would I make a half liter solution? I'm sorry, a half molar solution. So you're going to take 58 grams and divide it by 2, which is equal to 29 grams into 1 liter of water. All right, let me give you another one to work out. This is why I have the super long cord. Need a new, oh, it's not going to work, is it? Come on, come on, come on. Good. So if I have hydrogen, which weighs 1 and 1, carbon, which weighs 12, 6, atomic number 6, oxygen's atomic number is 8, mass number is 16. I want to know how to make a 0.5 molar solution of C6H12O6. Try to solve that. You need to determine the number, the atomic mass, convert that into grams, and then figure out how many grams you need to put into 1 liter of water to make a 0.5 molar solution. So this leads us into the idea of acids, bases, and buffers. All of this was building up to acids, bases, and buffers. Acids and bases are an environment in which organisms tend to find themselves, and they need to protect themselves from the effects of too many hydrogen ions or too few hydrogen ions. You encounter these in your life all the time. So to understand the idea of acids, bases, and buffers, you need to understand that water, a property of water, is that it will spontaneously ionize at room temperature. Now, when I say ionize, I mean water, H2O, will become two ions. One ion is H+. That would be the cation. The other ion is OH-, hydroxide. That is the anion. So it spontaneously breaks itself apart, leading to an equal number of hydrogen and hydroxide ions in a pure water solution. So this is the property of water at room temperature. Pure water at room temperature. Water with absolutely no solutes in it. It is unlikely that you have come in contact with this type of water before. Most water that you deal with has something dissolved in it. Heck, anything you get from a tap has some dissolved minerals in it, definitely has fluorine in it, all sorts of ions. This only applies to absolutely pure water at room temperature. And because of that, at room temperature, pure water will always have 7 moles, or it's a 7 molar solution of hydrogen ions. 10 to the minus 7th molar solution of hydrogen ions, and 10 to the minus 7th solution of hydroxide ions. They equal each other. You have just as many hydrogen as you have hydroxide, and it's equal to 10 to the minus 7th molar, which is a small number. That's 0.1, 2, 3, 4, 5, 6. That's how many grams of hydrogen are in one one molar solution of pure water at room temperature. The problem comes into play when you add solutes. Solutes will have an enormous impact on the number of hydrogen ions present. If a solute dissolves and releases hydrogen ions, gives off hydrogen ions, it's called an acid. If a substance dissolves and absorbs hydrogen ions, takes them in, or releases hydroxide ions, it's called a base. You know you're going to be asked at some point, what's the difference between an acid and a base, or what is an acid? I do not want to ever see any of you put an acid is something that burns you, or anything puerile like that. When I ask you what an acid is, I want to know that an acid is a solute that releases hydrogen ions, H+. By the way, you might also see it if you got a hydrogen ion, right? So you've got hydrogen has a proton here and an electron going around it, right? If it's H+, it means it has no electrons. So what is another word for a hydrogen ion? Okay, let me write that again. Sorry, I think I went too fast. You got a hydrogen in its stable state, just hydrogen is a proton and an electron orbiting it. Does that make sense? There's no neutrons or anything like that. If it's a hydrogen ion, a positively charged hydrogen ion, that means it has no electron. So what else could you call a hydrogen ion? A proton. That's exactly right. You're going to hear it from different instructors in different ways. I use the term hydrogen ion. Mr. Herndon always calls them protons. Dr. Balfour will alternate between the two. I have no idea what Ms. Merrick's or Ms. Scobe will call them. Let's see. So some examples of acids that you've seen in your life are orange juice, vinegar, apple cider vinegar. These are all solutes that, when dissolved in water, give off hydrogen ions. You've had orange juice before. Did it burn a hole in your stomach? Probably not. If it did, you'd be dead and wouldn't be in here. Vinegar. You've had vinegar. So, funny story. Apple cider vinegar, even though it says apple cider on it, and it looks cool and refreshing if it's in the refrigerator, does not taste at all like apple cider. So if you come in from, say, cutting the grass and you're very thirsty, Don't grab that and think you're getting anything good. That's what they say. I don't believe it. Solutes that dissolve and absorb hydrogen ions are called bases. So think Clorox bleach, sodium hydroxide, baking soda. You have two classifications of acids and bases. You have strong acids and bases and weak acids and bases. A strong acid will completely dissociate when placed in water. So if you had a big pile of hydrochloric acid, HCl, you'll notice that it is completely bound up there. There's no water in this container on the left. When you add water, all of those bonds break. You have 100% ionization. All of those molecules break into ions. That releases a whole bunch of hydrogen. For every chlorine atom you have, here, you release a hydrogen ion. So these are very, very strong if they are 100% ionized. They break apart. They become ions. Weak acids and bases, on the other hand, only partially ionize. Here's acetic acid, vinegar. Back to vinegar. Here, you've got your acetate and your hydrogen. When you add water, some of the bonds break, but not all of them. So you have a relatively fewer free protons, free hydrogen ions. So strong acids and bases are going to dissociate and release a whole bunch of protons. They release a whole bunch of ions, whereas weak acids and bases only partially dissociate. They release a lot less protons, a lot less hydrogen. Strong acids and bases versus weak acids and bases. Now, the hydrogen concentration in a substance can vary dramatically. You can have 1 mole of hydrogen. That's a very, very, very strong base. I'm sorry, very, very, very strong acid. Lots and lots and lots of hydrogen equals a super strong acid. To very, very, very little bits of hydrogen. Here you got 10 to the minus 14th molar of hydrogen. Teeny, teeny, little tiny bit. That's a very, very strong base, or very, 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 it's not even an acid, it's a very strong base. You do not want to write down all of these numbers. You want 0.00000000000000001 molar. You don't want to write that. Nor do you want to write down all the time 10 to the minus 14th moles. You want to simplify it. So to simplify it, we put these concentrations of hydrogen through a transformation process. And that's where we get this term pH. P usually, anybody know French? Anybody know French? Okay, neither do I. P stands for power in French. I thought it was poisson, but then I remembered, again, Little Mermaid, and that's actually fish. So, P stands for power. There it goes. So same thing in English, right? Power of H. And what's the H stand for? Not trying to trick you. Hydrogen. Power of hydrogen. And that's going to equal the negative log base 10 of the hydrogen ion concentration. I do not expect you guys to be able to do negative log base 10s in your head. Thing is, you won't need a calculator to do them. Because if you look at the negative log base 10 of any exponent, the answer equals that the reverse of the absolute value of that exponent. So if I was to take the pH of the negative log base 10 of, say, 10 to the minus 14th power, I end up with the pH equaling 14. If I have the pH of negative log base 10 of 10 to the minus 10th power, my pH is 10. If I have a pH of negative log base 10 of 10 to the minus 2 power, what's my pH? 2. Does that make sense? You're just looking at that exponent. What that means is, for you, and the big trend you have to be able to look at, is that the more hydrogen ions present, the higher the amount of hydrogen ions, the lower your pH. The more hydroxide ions, or the less hydrogen ions, the higher your pH. So you can set this up along a scale. It's called, go figure, the pH scale. At the very, very top, we have 0. 0 means a super low, it's a super low pH. it has a hugely high number of hydrogen ions present. See, battery acid's way up there. Do you want to get battery acid on you? No, because it's got so many of those hydrogen ions. As you go down from 0 to 1, you've decreased the number of hydrogen atoms by 10 times. So battery acid has 10 times more hydrogen ions than gastric fluid. Gastric fluid is stomach acid. You ever puked? It hurts. It hurts because you've got a lot of hydrogen ions coming up through your throat. Going farther down, you've got lemon juice. Lemon juice has about 10 times less hydrogen ions than gastric acid, stomach acid, or 100 times less than battery acid. You can eat a lemon and not die. Works out. Going down, you see vinegar and orange juice. I didn't realize beer was acidic. Coffee, acidic. Heck, rain is acidic because when pure rain, water, when it mixes in the atmosphere, it's mixing with carbon dioxide to create carbonic acid. And then you hit pH of 7. 10 to the minus 7th power equals a pH of what? 7. 7 is absolutely pure water at room temperature. It's termed neutral. So at the top you have acidic. You get 7, you've got neutral. At the bottom you end up with less and less and less hydrogen, more and more and more hydroxide, and you get basic. So you go to seawater, blood is slightly basic, baking soda, milk of magnesia, and then we get some dangerous stuff. Ammonia. You don't want to drink ammonia. That's disgusting. Bleach. You know not to drink bleach, I hope. Household lye. It's not just acids that are bad for you. Bases can be really bad for you too. In fact, if you ever wanted to get rid of a body, you just need about an 8-inch drain and a whole bunch of lye. Put on there, wait about 3 weeks, fine. Know where to find it. Not that I'm encouraging you, but now you know. Now, pH can impact biological systems dramatically. It alters the shape and function of molecules. All right, if you change the form of a molecule, what else have you changed? You change the form, you change the function. So any function this molecule may have has been altered if you change the pH. That will mean that molecules involved in chemical reactions can't react as well. They are being disturbed by the pH, so the chemical reaction rates will drop. Your two molecules may not be able to bind to each other because all those hydrogen ions are binding to where the molecules should bind. It changes the shape, it changes the form. And when that happens, you change the function. Ions are suddenly not going to dissolve as well in water because instead of having this glucose with these negative hydroxyl units, now those negative hydroxyl units are taken up by hydrogen atoms. So the water doesn't get in there to bind. Suddenly, water no longer breaks apart sugar. We have to maintain a consistent internal pH. Your body can withstand a pH range about 1 to 1.4. You can have 10 times too many or 10 times too few hydrogen ions. But once you get beyond that, that's where you start to fall apart, literally. Your body cannot handle ranges outside of that. You start to go into like ketoacidosis and all these other disorders. Adding just a little bit of an acid will have an enormous impact on a system. Your body has to remain constant. You have to maintain homeostasis. So to do that, you're going to minimize fluctuations in pH using buffers. A buffer is a molecule that either takes in hydrogen ions or releases them. That's it. Again, sort of like it's like antioxidants in that regard, except it's not donating electrons. Now it's donating hydrogen ions or taking them in. And that stabilizes the system. It lets that system achieve equilibrium. Buffers are going to be the focus of one of your labs coming up. I think it's next week's lab. Got a whole lab all about the importance of buffers and how they work. The way a buffer ultimately works is you're going to take a weak acid and its corresponding salt and combine them together, and they're going to reach a state of equilibrium. If you have too many H2CO3s, suddenly, or if you have too much hydrogen, suddenly those hydrogen ions are going to bind to HCO3 to make H2CO3, taking hydrogen ions out of solution. If you have too few hydrogen ions, that will break apart to yield that. You reach equilibrium. You reach an equalized state. Go forwards and backwards. So buffers are going to donate or accept hydrogen ions. And as they do that, they minimize changes in pH, so that when you drink a glass of orange juice, it doesn't burn a hole through your gut. That would be disgusting. Thank you, buffers. Do you guys have any questions? Perfect timing. If there are no questions, please go through the content review questions. I'm assigning your big question now, so it will be due 1 week from today. So this is the big question about chemistry and water. Will be due 1 week from today. Pardon? So next Thursday. Also, please note that you have a pre-lecture quiz. If you're doing those, that will be due at the start of the next class. It is the organic chemistry.